Okay, I think we're ready to get started, and we're going to hear about writing Instagram filters from Michele Pratusevich. Thank you.
Thank you. So, hi everybody. This is my first time giving a talk at PyCon, and I'm really excited to be here to tell you about how to make Instagram filters in 15 lines of Python. If you want to follow along on your mobile device, I recommend that you go to this URL, tilt your screen sideways. You can zoom in and look at the full resolution of the images on your own devices rather than on these projectors. So by day, I do computer vision research at Amazon. By night, I maintain a Python basic exercises blog. You will go to the blog to visit these sites, so hopefully you can check that out. I do have to say that I'm not affiliated with Instagram, so anything I say, Instagram is not behind it. I do these filters how I do them, not how Instagram does them. I just say that this is Instagram filters because that's how we understand it. So let's get started. How many of you actually use Instagram? Cool, yeah, me too. And I think one of the really cool things about Instagram is that when we put these filters on our images, we add basically a story. We want to transform the images to say something different than what we took, because clearly all of our images are boring and all of Instagram images are really fun. So hopefully you'll figure out how to do that throughout this talk. Here's an example. We'll see if this projector actually works. If you take an image of the countryside, beautiful, I want to be there right now. You pop our Instagram filter on it, and it'll turn a little bit redder, it'll get a little sharper, and in general, I want to be more in the left image than in the right image. So what we're going to do is we're going to walk through the Python code you need to create this particular Instagram filter. It's called the Gotham Filter. How many of you were early adopters of Instagram? Any early adopters? Okay, so if I say Gotham Filter to you guys in the audience, you're going to say, wait a second, the Gotham filter is this crazy black and white, like super, black and white filter. You're right. Black and white filters are more boring. I think colors are cooler, so I'm just going to do the Gotham filter, but in color. So I hope you guys will forgive me, you early Instagram adopters. So let's, without further ado, let's get started. The talk is structured in 4 parts. So first, I'll go over some of the basics of images that you need to know, just so the rest of the talk has some context. We'll walk through the basic building blocks of any Instagram filter. I'll show you how to use those building blocks to make the Gotham filter. And then I will show you that you can do this in 15 lines of Python. All right, step 1. You have to have an image. Go take a picture, upload it to your computer, get it into Python. My favorite image library to use is scikit-image. It has this really weird thing with imports. I don't know why. I hope to find somebody who's written scikit-image here at this conference to ask them why I have to do this. But I'm importing scikit-image, I'm importing I/O, and I just read my image. I don't want to have to worry about how is the image stored in memory. I'm just using scikit-image's library. It does a really great job. So we've loaded our image. What is the image actually made of? This is really important for us to understand before we can start manipulating it to make these Instagram filters. So if you zoom in really, really hard into that image, you will see that it's made of these things called pixels. What is a pixel? A pixel is 3 numbers, one of which represents how much red there is in the image, one represents how much green there is, one represents how much blue there is. So you'll see people talk about Rgb images. This is what they're talking about. Images are made of pixels. You have a red, you have a green, and you have a blue. And this is, the whole image is composed of these. Now, pixels are stored in something called the uint8 format. You don't need to know anything about it other than it's a number between 0 and 255, not including floating point. So there's 256 possible numbers that any pixel value can take. So red can be anywhere from 0 to 255, so can green, and so can blue. For anybody who does math, you know that integers are kind of annoying because when I want to divide things, they don't stay as integers. So the fact that we have only these 256 discrete values that every pixel can take is going to be problematic for us, because we're going to be multiplying by floats, we're going to be dividing by things. We can't just use 256 values to represent our images, even though that's how they're represented on disk. So what we have to do to make our images more manipulatable is use this fancy scikit image function to convert our image to floats. The cool thing about floats is that I don't just have 256 options for my pixel values. They can be anywhere in the range from 0 to 1. In this case, what it does is it converts the pixel values from uint8 to float, which means mapping the range 0 to 255 to 0 to 1. And the only reason I need to do that, again, is so I can do division and multiplication and get any kind of value between 0 and 1 rather than just these discrete buckets. It's a detail, but it's an important one. So now that I have these red, green, and blue channels, what I often want to do in image processing is look at each channel separately. And I can just leverage the fact that when scikit image loads my image, it loads it as a numpy array, however you want. I don't particularly care. So I can separate out my red channel, my green channel, and my blue channel separately. It's just that it's a bunch of stacks of images. That's exactly how I can think of it. So I can take my image and look at each of those channels separately. And if I manipulate them and whatnot, I want to be able to take those 3 channels, put them back into an image so I can see what the result is. So of course, we need the opposite version of this function. Rather than splitting the image, I want to merge it back. And you can see the code for how to use these two at the bottom there. I'm leveraging a lot of stuff in these code samples. As a note, I basically am leveraging the fact that NumPy works as arrays. Images are 3-dimensional arrays. The color channel is in that the last side of that array. Yeah, you can look at the NumPy documentation for exactly how NumPy stack works, but it's just smushing the image channels one on top of the other. Okay, so now that we have our image channels separately, we're going to talk a little bit about this concept of image histograms. So how many of you have used something like GIMP or Photoshop? Okay, now keep your hands up. How many of you know how to use GIMP or Photoshop? Okay, good, that's what I thought. I don't know how to use them either. So but one thing I do know is that when you load an image into GIMP or Photoshop, you see these histogram things that show up. So I want to talk about what they actually represent. Now this is related to the image channel discussion we were just talking about, because as we know, every image is made up of a red channel, a green channel, and a blue channel. One way to visualize what those pixel values are doing is through these image histograms. So a histogram, just like you would see in any high school math class, high school statistics class, is just a frequency representation of how often that number appears in that particular array or image or what have you. So on each one of those histograms, on the right-hand side is 0. And on the left-hand side, because we converted our image to floats, is 1. So you can see that this particular image, there's a lot of blue. It's a seaside. There's a lot of blue pixels that are really, really dark blue. They're towards the left-hand side of that blue histogram. So there's a lot of blue in this image. There's also, however, a ton of red and a ton of green, because we're looking at each of those channels separately. One thing to keep in mind when you're looking at histograms is that because images are stored in uint8 format, there's really only 255 possible values that any pixel can actually take. So if you want to plot these histograms yourself, you might want to add the bins equals 255 into your histogram code to make sure that you get reasonable histogram representations. So this is exactly the kind of histogram you'll see if you load up an image in GIMP or Photoshop. The reason that we're talking about these is because a histogram is a great way to visualize what's happening in your image channel. The next thing I'm going to show you is how you look at this image histogram and modify it to see what's going on in the image. Oh, that being said, let's move on to these basic building blocks of Instagram filters. Every Instagram filter has 2 major components. One is sharpening and blurring, which we'll talk about how to do that. And the second is channel interpolation of these image histograms. We'll go through these one by one, and then we'll put them all together at the end to make our Gotham filter. So let's talk about sharpening and blurring, specifically blurring first. That's kind of easy to understand. So if we take an image and we want to blur it, the way that this is typically done is you use what's called a Gaussian blur. A Gaussian blur is essentially a weighted sum of neighboring pixels. The reason we call it Gaussian is because the center pixels of my window are weighted higher than the pixels on the outsides, but that's really not very important. Just know that it's a weighted sum. Oops. I'm not going to implement this myself. I use, of course, scikit-image. It implements my Gaussian blur function. It takes 3 arguments, my image, my sigma, and I'm just saying operate on the whole image altogether, Rg and B, don't do the channels separately. The sigma basically represents how wide of a window you want to do on your blur, so the bigger the value of sigma, the more blurry your image is going to look. So here's an example. You can see that the image on the left is much more blurry than the image on the right. I don't remember what sigma value I used here, but the point is that the larger the sigma, the more blurry the image. Okay, image blurring, why do we care? Why do our Instagram filters have blurry images in them? The answer is they don't. But the thing we want to do is sharpen images. How do you sharpen images? Well, we just learned how to make them more blurry. Why don't we do that and just subtract that blurry component away from my original image? That's all that sharpening is. We take our image, we blur it, and we just subtract out the blurry bits. In theory, all that's left is all the sharp stuff. There's a little bit of trick to this, and I'll walk through the code here. But the basic idea in sharpening an image, we blur it, we take out all the blurry bits. So the first thing we do, you can see the line that does the blurring. It's exactly like we just talked about with image blurring. And then in the next line, all I'm doing is subtracting out the blurry parts of my image. The tricky part with this is that I have these 2 parameters, A and B. Those are like my mixing parameters. How much of the original image do I keep? How much of the blurry bits do I take away? If I take away a larger fraction of my image than I'm leaving, my image is going to have some white balance issues. It's going to be too dark, it's going to be too bright, whatever. So you want to just make sure that A and B sum up to 1. I guess in this case it's A and negative B because I'm subtracting out the blurry part of my image. And the reason I have this numpy.clip around it is because, as I said before, images are only in this particular range of values. Because we're dealing with floats, the pixel values have to be between 0 and 1. So I'm just making sure that in case in my subtraction and multiplication of my blurry image, I have a value outside the 0 and 1 range, that I always have pixel values that are valid for my image. And the result of this is that I have an image that's much sharper. So again, all I did, I blurred my image, and I just took away the blurry parts to leave my sharp image. And here's what it looks like. I hope you can see it on the projector. If not, take a look on your phones. But if you look at the detail in the water, for example, you can see that it's a lot crisper. And all I did here, again, was I took the blurry part of my image and subtracted it out from the original. Image sharpening is super important in a lot of filters because clearly we can never take super sharp images. I've never seen a filter that doesn't have some component of sharpening. All images have to be sharper. It gives it a little bit more pop. So now that we've done the image sharpening and blurring, let's look at the second component of Instagram filters. This one's a little bit more complicated, so I'm going to spend a little bit of time on this slide walking you through how to manipulate these image histograms so we can build them up into our Gotham filter. So we were talking about histograms being a representation of how much of each of those pixel values exist in the image. You see on the right-hand side here, I'm calling that the before histogram. This is the red channel of that seashore image that we saw in the previous slide. It looks pretty normal. There's some red, there's some zeros, there's some ones, and it has some distribution. But what I'm doing on the left-hand side is I'm stretching out the histogram. That green dot kind of gives you an anchor point. Instead of the anchor point being in the center of that histogram, I'm taking that green dot and sliding every pixel value from that green dot to the left-hand side. So I'm smushing everything towards the darker reds. If this is the red histogram, what I'm doing if I'm moving that green dot is I'm turning a lot of the values that are a little bit red, a lot more red. I'm infusing this image with a lot of red. And the reason I'm showing you this in histogram space is that that's what you see on the histogram. You see that on the left-hand side, there's a lot more red on that histogram. The red dots are just giving you the anchor points. The red dots are not moving anywhere. So what I'm calling this transformation is channel interpolation. What this means mathematically, we'll see in a second. But you can just imagine that the same way you do in GIMP or Photoshop, if you take one of those anchor points and you slide it, you're just moving the distribution of pixel values from one end of the histogram to the other. But we don't understand what histograms mean. They're super hard to make into real images. So let's see what this exact same transformation looks like on an image. You can see that the image is a lot more red. I just pushed a lot of those pixels into the higher concentration of red space. So if I apply this transformation independently on every pixel, the result is that this particular image turns a lot more red if I'm applying this to the red channel. The code to do this is a little bit complicated, but here it is. The operative piece of code is, it actually happens inside this NumPy interpolation function. So what I'm basically doing is I'm specifying a set of these anchor points. I'm specifying the points 0, 1, and some numbers in between that specify how I'm stretching all of these different components of my histogram. And this is why this is called channel interpolation. Because mathematically what this function is doing, it's taking my range of values from 0 to 1, chopping it into some number of pieces, and then reinterpolating each of those pieces as a different linear function. I don't have to worry about any of that. NumPy is taking care of all of this for me. All I have to worry about as a filter designer is what are those new anchor points on my histogram. If previously my anchor point was in the middle, it was just a straight histogram, whatever I had, I changed that anchor point closer to 1, I add more red to my image. That's all I have to know as a filter designer. And you can see this all together here. So this particular transformation turns this image a lot redder. And all I'm doing is I'm moving one of these anchor points from 0.5 to 0.8. So you can see when I'm calling my channel adjust function, I'm specifying 3 anchor points. I'm specifying 0 and 1, which are the ends of my range. I don't want to change those. I always want to have values from 0 to 1. But then I'm saying every value from the center is going to get smushed a lot more into the red domain. So you can see what the histograms and the images look like as I move that anchor point forward. Now this is pretty straightforward to visualize for one value, one anchor point that I'm changing. Instagram filters in general are a lot more complicated. There's a lot more subtlety. There's a whole kind of artistic, creative way of designing these filters by moving these anchor points in different ways. I'm not a designer, so I understand the math a little bit better. But I think it's also important to see how this impacts the image and the histogram. Once you have an understanding of how the representation is in histogram space, you have a little bit better understanding of how to put all of these things together into one image. So now that we've built up our 2 basic building blocks, sharpening and blurring, and channel interpolation, let's go through how we would actually make the Gotham filter. As you can imagine, it's just a combination of all these different basic building blocks. So based on my experimentation and by looking at some sources on the internet, this is essentially what the Gotham filter is. It sounds like a bunch of gobbledygook, but we'll go through and show it up in code. So the first thing we're going to do is we're going to boost the contrast in the mid-tones. We'll see what that means in channel interpolation space in a second. We're going to make the blacks a little bit bluer. We're going to sharpen the image a little bit, because again, every image has to be sharpened. We're going to boost the blue channel in the lower midtones, and we're going to decrease the blue channel in the upper midtones. And we'll do all of these with the basic building blocks we just built up. So the first thing is we're going to add a midtone contrast boost. So you can see that my call to the channel adjust function is a lot more complicated than moving one anchor point. But if you look carefully at what those values are, you see that 0.5 stays 0.5. The only things I'm changing is the space around 0.5 and the space around 0 and 1. So I'm stretching and squeezing, I'm stretching out the values in the middle of that range, in this case on the red channel, and I'm squeezing the range on the low end of the value, 0, and the high end on 1. And then I merge all my channels back together, and I get an image. So you can see that the after image, the sky is a little bit redder. It's kind of hard to see on the projector, I'm sorry. But again, if you look on your phones, you can see it. So this, I'm adding a little bit more red to my image because I'm squeezing those values close to 1. Okay. The next thing is I'm going to make the blacks a little bit bluer. So this is I guess I should have included this in my original building blocks of Instagram filters because we did not technically go over this. We can go over it now. So we want to take our blue channel and we want to add a little bit more to every blue value that we have. So if there was a value for, if there was a blue value of 0, it's now a little bit blue. If there was a really high blue value, I'm going to make it even bluer. And again, I want to clip those values between 0 and 1, because I can't have values in my image outside of 1. The adding a little bit of blue, or a little bit more blue to your blue channels gives it the kind of the moonlight aura in a lot of these filters. The next thing we're going to do, do a little bit of sharpening. So I'm going to use the mixing parameters of 1.3 and 0.3. You can see in the leaves around this picture that they're just a little bit crisper. So I'm subtracting out 0.3 parts of my blurry image from 1.3 parts of my non-blurry image to sharpen my image just a little bit. And the last thing is I'm going to boost my blue channel in the lower midtones and decrease in the upper midtones. So this again looks like a really horrific histogram adjustment, but it's really the same thing that we were doing before. It looks like a ton of random numbers, but you can see what's going on is that the center actually got moved. So I'm shifting everything away from the center. The boosting in the lower midtones just means that all of the values in that range of 0.25, kind of in that bottom corner, get stretched out. And the upper midtones, around the 0.75, they also get pushed out. And the reason I want to do this is because drastic colors in my filters are a lot more interesting than dull, boring colors. And again, at the end, I want to reconstruct all of these back into my original image. And you get a lot of images that look a lot more interesting. You add interesting reds, you add interesting blues, you make them darker, you add a lot more pop. So if you wanted to do this on your own images to make your own filters, you could either scroll through the filters on your phone, or you can think about how those histograms get adjusted. So in that top row, you see that the sky turned a lot redder. I think that's a lot more interesting of an image. I think just looking at the blue sky is kind of boring. You want to add a little bit of interesting surrealist color to your filters. I think the sharpening adds a lot of value to your photos. If you make your images a little bit sharper, you can see a lot more detail, and it's really simple and straightforward to do. So, as I promised in the title of this talk, you will get 15 lines of Python to make the Gotham filter. I did have to use only one function. Other than that, I could do it all in 15 lines. But you can see that this is all of the steps that I just took you through and showed you all the intermediate images. The meat of the work is done by this channel adjustment, channel interpolation function. I highly recommend that you go back to your interpreters and check out the interpolation function from NumPy to figure out how exactly it shifts around your histograms. I recommend that you never write code like this to ship into production, because this is obviously hard to read. But if you wanted to make Instagram filters, you could do it in just 15 lines. There's tons of resources online for how to manipulate images, for how to make Instagram filters, you could look at these slides, you can look at these images, send me questions, I'm happy to answer them. I hope that every one of you goes back and plays with images, makes your own filters. figures out how to translate them to a filter that I can use on my phone. There you have it.
So now we have some time for some questions. So if you have a question, if you can walk up to one of the mics.
Yeah.
Like curious how you came up with the values to use in your in interpolation. Like, is there some other kind of way you could programmatically come up with an array like that, or was it just experimentation?
I found a blog post that had done it in HTML and CSS, and then I tweaked the values a little bit to make it look better. The problem with computational photography and image processing in general is there's a really hard way to automate whether an image looks good. So if the filter looks good, like, yeah, okay, the number looks good, and I don't really understand why. So if I know that I want more blues, I want to shift my blue values all the way to the right, but beyond that, it's really hard to tell. I will rely on designers to do that rather than people like me. Yeah.
I was just wondering if you'd looked at integrating any type of object detection or image segmentation, and how this type of process would integrate with that additional process, something like diptych. If you've seen the diptych application, something like that, and how this could integrate with that.
You mean applying different filters to different parts of the image based on where
on
the
the
objects are?
segmentation, yeah, exactly.
Sure, you can definitely do that. The only thing you'd have to do is specify what part of the subimage you want to apply it to. So even in the functions that I've showed you here, you don't have to pass in an image. You can pass in the subimage and reapply it back. Object detection is kind of a whole field unto itself. Once you solve that, you could totally manipulate different parts of the image differently. The thing I would be worried about is at the boundary of the object and the background. That's the only thing I would be worried about.
Thank you.